Today, let's talk about AMGM inequality. Let n be a natural number. Let a1, a2, up to an be non-negative real numbers. Then we have the following result: a1 plus a2 plus blah 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 plus an divided by n is greater than or equal to a1 times a2 up to an, and then take the nth root. This part is the arithmetic mean, am, and this part is the geometric mean, gm. So let's prove the statement. If all of the a1 up to an are all 0, then am is equal to gm is equal to 0. So we can assume without the loss of generality that a1, a2 up to an are not all 0. Then in this case we know that am is greater than 0. Let capital An be the arithmetic mean of the first n numbers. So an equal to a1 plus a2 plus blah 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 plus an divided by n, as capital An plus 1 and capital An are greater than 0. We have an plus 1 over an minus 1 is greater than 0 minus 1, which is negative 1. Let's recall the Bernoulli's inequality. If x is greater than negative 1 and n is a natural number, we have 1 plus x to the power n is greater than or equal to 1 plus nx. So we can apply Bernoulli's inequality here. We know that an plus 1 over an to the power m plus 1 is equal to 1 plus an plus 1 over an minus 1, and then to the power m plus 1. By the Bernoulli's inequality, we have this statement: 1 plus n plus 1 an plus 1 over an minus 1. And this is equal to 1 plus m plus 1 an plus 1 over an minus bracket m plus 1. And this is equal to 1 plus m plus 1 an plus 1 over an minus n minus 1. So we have positive 1 and negative 1, so it cancels out, and we are left with m plus 1 an plus 1 an minus n times an. We know that an is equal to a1 plus a2 plus blah 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 plus an over n. We have an plus 1 an plus 1 is greater than or equal to an plus a2 a1 plus a2 plus blah 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 plus an plus an plus 1 minus a1 plus a2 plus blah 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 plus n divided by an, and this is equal to an plus 1 over capital AN. So by rearranging the terms, we know that capital AN plus 1 to the power n plus 1 is greater than an plus 1 over capital AN times an to the power n plus 1, which is equal to an plus 1 times capital AN to the power n. We want to show that an to the power n is greater than or equal to a1 times a2 times blah 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 times an. We just use induction. When n is equal to 1, we have capital A1 is equal to A1. So the statement is true when n is equal to 1. Suppose the statement is true when n is equal to k for some positive integers k. That means ak to the power k is greater than or equal to a1 times a2 times blah 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 times ak. When n is equal to k plus 1, ak plus 1 to the power k plus 1 is greater than or equal to ak plus 1 times ak to the power k, according to this part. Also, by the induction hypothesis, we know that ak to the power k is greater than or equal to a1 times a2 times blah 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 times ak. We know that this is greater than or equal to ak plus 1 times a1, a2, blah 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 up to ak. So the statement is also true when n is equal to k. By the principle of mathematical induction, we know that an to the power n is greater than a1, a2, blah 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 up to an for all natural numbers n. So we arrive at the final conclusion that capital AN is greater than or equal to a1 times a2 times blah 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 times an, and then taking the nth root. So this marks the end of the proof. If you find my video interesting, please consider subscribing my channel, liking my video, and commenting down below. Thank you. See you in the next video.